Hi, I'm Charles Hamilton. My student number is 218-237-214, and it's March 29th, 2022. Today I'm going to be explaining, using the back of the napkin, the Doppler effect. Very important physical phenomenon that has many engineering applications. The most intuitive way to understand this, because we've all experienced it, is to imagine that you're standing on the side of the road and a car is coming towards you. As it's moving towards you, the car's engine is producing a sound, and that sound, or the sound waves, have a frequency. If the car were standing still and we were standing still, the frequency would be the same as the source frequency. There would be no change. But when the car starts to move towards us and those sound waves come towards us, the speed of sound is being added to the speed of the car. And so these sound waves actually bunch up in front of the car. And to our ear, the frequency is higher, resulting in a higher pitched sound, which you've probably noticed when you're standing on the side of the road. A car drives towards you, the sound seems higher pitch. And then suddenly, and we'll just draw another friend of ours back here, when the car passes us by, its engine is still producing sound, but now those sound waves are being the speed of those sound waves is being offset by the car still zooming along and away from the observer now. And so those sound waves are being stretched out. And so this is in essence the Doppler effect, the idea that the frequency that an observer experiences of sound waves or even radio waves changes depending on the velocity of the source of that wave relative to the observer. This can be expressed mathematically with the following formula. The frequency that the observer experiences is equal to the frequency of the source multiplied by the speed of the waves plus the velocity of the observer, which we can take as 0, divided by the velocity of the waves again, plus the velocity of the source. So this would be, the speed of our car here. So taking our speed is 0, because we're just standing there, we can see that this term will affect the source frequency to give us our observed frequency. Now, as the car's coming towards us, the frequency is higher. And so that's a result in this equation. We would be taking the velocity as a negative number. So this term would be greater than 1, and it would be a multiplier on the source frequency. This would result in a higher frequency, higher pitch sound. If the car was moving away from us, we would take this as a positive number. This term would be less than 1, and so we would only have a fraction of the original source frequency that we would observe, resulting in a lower pitch that we would hear. As I mentioned, this also works with radio waves, and it's in these applications, it's because of its effect in radio waves that its most popular applications are found. So, for example, in radar, we can determine if a fighter plane is invading our airspace, we can tell how quickly it's going, because our radar dishes are going to be sensing that those radio waves are bunched up, and so this plane must be heading towards us. Or conversely, if it's heading away from us and it's going in this direction, those radio waves will be further apart. Similarly, this is used in astronomy a fair bit to determine the speed of galaxies and stars. So I hope that was informative. Thank you very much.